네, 안녕하세요. 오늘 그 수업을 시작을 하도록 하겠습니다. 어, 사실 뭐 지금 역시나 이제 코로나 바이러스 사태 때문에 저희가 이제 수업을 그 교실에서 이제 진행을 하지 못하는데, 이제는 사실 제가 있는 오피스에 그 코로나 의심 환자가 발생했다는 해서 사실 오피스가 지금 폐쇄가 된 상태입니다. 음, 그래서 제가 이제 오피스에서 녹화를 못하고, 어, 집에서 이제 녹화를 해야 되는 그런 상황이 되었고요. 뭐 그렇기 때문에 제가 녹화를 할 시간이나 이제 장소가 그렇게 이제 마땅치는 않아서 좀 어떻게 녹화는 하지만은 이게 뭐 제 얼굴을 보여드리기가 그렇게 이제 쉽지는 않은 그런 상황입니다. 뭐 그래서 이제 뭐 전에는 요 구석에 제 얼굴을 조그맣게 이제 띄워놓고 뭐 강의를 이제 녹화를 했는데, 이번에는 그냥 그 슬라이드만 이렇게 보여주면서 제가 필기를 하면서 녹화를 하도록 하겠습니다. 뭐 어차피 여러분들이 슬라이드에 이제 집중을 할 것이기 때문에 뭐 그렇게 차이는 없을 거라고 이제 믿겠습니다. 뭐 어째 슬라이드에 이제 집중을 해서 들으면 되는 거기 때문에 별 차이는 없을 거라고 생각을 합니다. 우리가 이제 저번 시간에 그 사실 배운 것 중에 이제 가장 중요한 거는 요 branch instruction, conditional branch instruction 이 부분이 굉장히 이제 중요하고요. 왜냐하면은 우리가 이제 컴퓨터 프로그램에서 이런 컴퓨터가 단순한 그런 계산기, 그러니까 우리가 말하는 calculator 그런 역할뿐만 아니라 뭔가 이제 더 수준 높은 그런 어플리케이션 프로그램들을 수행할 수 있는 이유가 이렇게 보통 우리가 분기문이라고 하죠. branch instruction. 요 어떤 조건에 따라서 컴퓨터의 실행을 바꿀 수 있는 그런 명령어들이 이제 존재하기 때문에 컴퓨터에서 이제 돌아가는 프로그램은 일반 계산기에서 이제 돌아가는 프로그램과는 달리 좀 더 하이 레벨의 높은 수준의 이제 프로그램을 돌릴 수가 있는 것입니다. 이런 우리가 이제 브랜치 인스트럭션에 대해서 이제 소개를 하였고요. 그리고 이제 역시나 우리가 이제 프로그래밍을 할 때 또 많이 이용하는 것이 이제 펑션이죠. 뭐 펑션을 이제 우리가 이용을 할 수 있기 때문에 좀 더 이제 모듈러한 프로그래밍이 이제 가능하고, 우리가 또 많이 쓰는 이제 부분들은 따로 이제 펑션으로 만들어놔서 그 펑션이 이제 수행할 수 있도록. 그래서 우리가 뭐 프로그래밍 할 때 똑같은 라이팅을 계속 반복하지 않도록 할 수 있게 하는 것이 이제 펑션입니다. 펑션을 어떻게 이제 수행을 하느냐. 어쨌든 이제 펑션을 수행하기 위해서는 컴퓨터 하드웨어도 이 펑션 수행을 서포트를 이제 해줘야 되고, 그때 이제 이용이 되는 것이 이제 그 점프 인스트럭션이죠. 점프 인스트럭션인데 이제 펑션에는 우리가 이제 C를 보면 알겠지만은 C에는 항상 뭐가 있죠? 항상은 아닌가? 어쨌든 C의 그 펑션들을 보면은 잠시만요. 지금 태블릿이 잘 작동 안 해가지고 세팅을 해보려고 했는데 뭐 잘 안 되네요. 예, 그래서 이제 펑션은 이제 C 펑션을 보면은 항상 뭐가 있죠? 예, 그 펑션은 이제 데이터 타입이었고요. 이거 좀 이상하네요. 펑크가 있고, 그 다음에 어떻게 되죠? 여기에 이제 return 하는 것이 있죠. 잠시만요. 예, 좀 태블릿이 좀 이상하네요. 예. 어쨌든 뭐 진행을 하도록 하겠습니다. 예, 펑션을 보면 이제 뭐가 있죠? 예, return 타입이 있고요. return 타입은 이제 데이터 return 타입이 있고, 뭐 int라든지, 그 다음에 어떻게 되죠? 이 펑션 네임이었고, 그 다음에 펑션 내부에 return, 그러니까 펑션에서 돌아오는 부분이 있다라고 했죠. 예, 그렇기 때문에 이제 펑션에서 우리가 return을 해야 되는 그런 상황이 발생하고, 그것을 지원하기 위해서 jump and link라는 인스트럭션이 이제 사용이 된다라고 했습니다. 그 이제 리스크 5에서는 어쨌든 이제 그 링크, 그러니까는 리턴 어드레스를 이제 저장하기 위해서 점프 앤 링크 인스트럭션이 있고, 그 다음에 우리가 이제 저장을 해놓은 그 리턴 어드레스로 복귀를 하기 위해서 점프 앤 링크 레지스터라는 명령어를 지원을 하고 있다라고 했죠. 그래서 이제 example들을 이제 보여줬고요. 그 다음에 그 펑션이 수행될 때 그 펑션의 그 내부 variables, 그러니까 그냥 그 local variables는 역시나 이제 하나의 독립된 그런 프로그램처럼 이제 수행이 되게 됐죠. 뭐 그렇기 때문에 어쨌든 펑션이 이제 수행이 되면서 레지스터가 이제 오버라이트 되는 그런 가능성이 이제 생기게 되는데, 그럴 때 원래 이제 계산하고 쓰고 있던 레지스터 값들을 temporarily 저장하기 위해서 이용되는 것이 이제 스택 메모리라고 했었죠. 그래서 이제 펑션이 이제 콜링이 되면은 이런 것처럼 우리가 이제 스택 포인터를 업데이트를 해주고요. 그 다음에 스택에다가 원래 프로그램이 저장하고 있던 그 데이터를 그 스택 메모리에 옮겨주는 그런 역할이 프로세스를 이제 수행을 해야 되고, 펑션이 이제 끝난 다음에는 리턴을 하기 전에 스택에 이제 저장돼 있던 레지스터 값들을 다시 다시 이제 복귀를 시켜주는, 리스토어를 해주는 프로세스가 이제 들어가게 됩니다. 그래서 우리가 이제 그 부분들을 이제 뭐 example을 보면서 이렇게 했고요. 또는 이제 복잡한 펑션의 이제 형태가 이제 recursive 펑션, 이런 부분이 있죠. 그러니까 펑션 안에서 또 펑션을 다시 콜하는 경우, 뭐 이거는 우리가 이제 스택을 계속 증가를 시키고 또 링크 어드레스를 계속 스택에 이제 저장을 하면서 펑션 속에서 펑션이 리턴 할 때 다시 리턴 어드레스를 리스토어 시켜주면서 진행을 한다라고 했습니다. 뭐 그래서 이제 우리가 example로 우리가 보여줬던 것이 배웠던 것이 팩토리얼 코드죠. 사실 뭐 recursive function에서 가장 쉽다고 해야 되나요? 가장 이제 대표적으로 이제 나오는 example이 팩토리얼 function입니다. 그래서 사실 이 코드가 그렇게 이제 뭐 전에 말했듯이 그렇게 쉽게 이해하기는 어려울 수가 있어요. 처음 보게 되면은. 뭐 그렇지만은 이제 코드를 이제 잘 따라가다 보면은 이게 어떤 식으로 이 recursive function이 이제 동작을 하는구나를 알 수가 있을 겁니다. 뭐 기본적으로는 이제 똑같은데요. 그 펑션이 이제 호출되는 그런 부분들을 부분이 이제 계속해서 반복해서 이제 호출이 되기 때문에 스택을 점점 스택 메모리 포인터를 점점 업데이트를 해가면서 내부에 있는 레지스터 값들을 저장을 하고 다시 이제 펑션에서 리턴을 할 때 그것을 읽어가면서 변산을 이제 수행하는 거죠. 자, 그러니까 이 부분이죠. 리턴 할 경우에는 원래 아규먼트와 펑션의 리절트 값을 계속 이제 곱해가는 거죠. 그러니까 뭐 이 부분들이 여기 보면은 여기죠. 여기. 그러니까는 펑션에서 이제 리턴하는 값하고 스택 포인터, 요 아규먼트죠. 이거는 아규먼트고, 그 다음에 펑션에 이제 가지고 있던 세이브된 밸류, 그것을 여기 x6에 이제 저장하고 있죠. 뭐 그 부분들을 계속 곱해가면서 우리가 값을 계산을 하는 것입니다. 자, 여기 보면은 뭐라 그럴까, 이런 것들을 어떻게 이제 하나요? 뭐 그러니까는 어떻게 요 하이 레벨 랭귀지를 이렇게 어셈블리 인스트럭션을 쓰는 어셈블리 코드로 어떻게 이제 바꿔주는, 요거 역할은 뭐가 하죠? 컴파일러가 합니다. 컴파일러가 열심히 코드를 분석해서 이런 어셈블리 코드를 이제 제너레이션 하게 해주고요. 뭐 이때 이제 여러 가지 그런 옵티미제이션 테크닉이 이제 들어가게 됩니다. 컴파일러가 쓰는 옵티미제이션 테크닉은 뭐 여러 가지가 있는데 그거는 이 과목에서는 이제 배우지 않고요. 나중에 이제 컴파일러에 해당되는 과목을 들을 때 이제 배울 것이라고 예상을 하고 있습니다. 그래서 그 옵티미제이션은 무엇을 위해서 옵티미제이션 하느냐? 역시나 그 퍼포먼스를 증가시키기 위해서, 그러니까 퍼포먼스를 임프루브 시키기 위해서 이런 여러 가지 옵티미제이션 테크닉이 이제 들어가게 되는 거죠. 자, 지금 메모리 레이아웃이 이제 어떻게 또 구성이 되는지도 또 이야기를 했습니다. 이제 가장 우리가 이제 눈여겨봐야 될 것은 이제 스택은 메모리의 라스트 어드레스에서 이제 시작을 해서 이 방향으로, 그러니까는 스택 포인터가 마이너스 되는 방향으로 증가를 해야 된다고 해요. 디크리스 되죠. 다이나믹 데이터는 요거는 어떤 거죠? 우리가 이제 보통 C에서는 멜록, 그 메모리 얼로케이션 명령어가 있죠. 요 멜록 그 펑션에 의해서 다이나미컬리 그 프로그램 내부에서 선언이 되는 어레이라든지 이런 부분들이 이제 다이나믹 데이터가 되겠습니다. 다이나믹 데이터가 증가하는 방향은 요거예요. 네, 텍스트라든지 스태틱 데이터가 이제 존재를 하고, 리저브드 영역은 오퍼레이팅 시스템이라든지, 그 다음에 그 중요한 이제 시스템 영역으로 이제 남겨두게 됩니다. 그다음 이런 여러 특수한 프레임 포인터, 이제 스택 포인터 이런 것들도 이제 소개를 했고요. 이게 왜냐면은 그 펑션 내부에서 역시나 그 다이나미컬리 그 메모리 영역을 할당을 해주는 경우도 있죠. 그러면 이제 그 메모리 영역은 그 펑션 내부에서 이제 할당이 되는 거기 때문에 이게 완전 템포러리 영역이죠. 그래서 스택 메모리에 이제 저장을 하고요. 이 부분들을 이제 잘 관리를 해주기 위해서 프레임 포인터라는 것도 존재를 하게 됩니다. 됐고요. 네, 어드레스 모드까지 했고, 네, 그래서 이제 전체적으로 이제 코드가, 그 하이 레벨 랭귀지가 어떤 식으로 이제 트랜슬레이션 되는지 이런 부분들을 또 이야기를 해보도록 하겠습니다. So this time I will explain about the translation of the high-level language and then how the program start in the computer hardware. So this is the translation step of the normal C program. The first, this C program language, C program code is just the text code. So that means that this C original program can be edited by the text editor. It's just the text. It's a program, but it's just a text program. So it's a data. But this high-level language, the computer hardware cannot understand this high-level language. Computer hardware only can understand the machine language represented by the binary number. So this high-level language should be compiled by compiler. The compiler translate this high-level language program into the assembly language program. So assembly language program is this program is just also the text program, but this assembly program exploit the assembly instructions. And then these assembly instructions can be mapped to the machine language one-to-one, nearly one-to-one. Not every instruction, but this assembly language programs, actually these assembly instructions can be mapped to the machine language one-to-one. And then this assembly language is also compiled by assembler program. So this machine language module object code is generated. So this is the some compilation step. But so what compiler can we use? So actually, if we write the code with the C program, actually the most famous compiler is the GCC, GNU-C compiler. So if we compile the code with the GCC compiler, then what is generated? actually the execution code is generated finally, but in the some intermediate step, the object file like a .obj file is generated. So this object file is include the machine language module, and then also when we compile the C program, some program needs the some libraries. So when we actually the very simple example for first program is the hello world, but when the hello world is written, then we need to include a standard IO library in the as the header of the C program. So this library also is required to generate the binary code. So this object code is generated from the original uh, uh, our high-level language code, and then the compiler uh, combine the object file from the other libraries. So also, this libraries also has some object code, and then these libraries include some machine language code. So what is this step? So combining these different object file is called the linking. So and then this application is called the linker. So this linker combines the many object files and then generate the binary execution file. So this binary execution file includes all machine code from my my program. Also, this binary code include some machine code from the libraries already made libraries. Then by combining these libraries and my library, then execution time, the binary code is generated. So this binary code is just the data. So I already explained that the machine code can be represented as the binary data. So it's similar to the normal data. So this binary code is actually stored in the storage device like hard disk drive, also SSD as a file. And then we execute this binary file, then operating system read this binary data from the storage device, and then fetch this data into the main memory. So it's the loader is here, then it's the object of the loader is to transfer this binary data as a binary code to the main memory. So this is how the binary code is generated by the compiler, and then how this binary code is started in the computer machine. So actually this slide explains the some operation of the compiler, some normal compiler. So the first step by the compiler is to generate the object code as I mentioned. So this object code includes these informations. So what is included? This is a header file. The object file includes the header. Header describes some content and then some information of the object module, and then text segment is some instructions. So assembly instruction what's this? This text segment include the assembly instructions or machine code instructions actually. So this text segment is just a set of instructions which is translated by the compiler. And then static data segment. The static data is such as the a equal 1. So this simple, actually a equal 1 can be included in the instruction, but some data can be also included in the code, like a equal 건지 is text data. So this text data, if or some state data can be included in the as the part of the program. So this static data is also included in the program. And then relocation info. This is relocation info is the some include uh, include some information about some loaded libraries. So for example, if we use the printf function, and that this function is included in the standard IO libraries. So actually, this function is we do not write the operate code for this standard function, but standard function is already made by other programmers. But and this if we want to use this printf function, then this information about this library should be included in our object file. So it's a relocation info. So this is some address for the library, some address location of the some function, and then function included by the other libraries. And then the symbol table is some global definition or some external reference is included in the symbol table. And then for debugging, the debugging info is also included in the object file. And then so linking object module. This linking, what's the linking? So linking is combining different libraries, and then these libraries include the machine code. So linking is just combine this other machine code and from the other libraries. But actually, we will learn about the virtual memory later in the memory hierarchy chapter. But if the virtual memory is used, then the programmers or compiler need to manage the address of the each data type or the address of the function manually. So the linker also manage some address of the other libraries or other functions. But as virtual memory is used, so compiler does not need to do this process, and then the memory address is managed by the operating system. So loading, this is some step to load the program from the storage devices. So let's see some steps. So actually, to load the program is to read the file, the binary file from the disk, and then get the some code data into the main memory. So the first step is to read the header to determine the segment sizes, and then if we so the operating system analyzes this binary code and then create the virtual address space. So the memory is managed by the operating system, is my OS operating system. So virtual address space is allocated to the programs. And then in order to execute this program, some static data and then instructions should be loaded to the main memory. So this text and some required data, initialized data, should be transferred to the main memory. And then so stack memory is set up by operating system, and then the register file is also initialized. So until this step 5, the operating system prepare to start the program. So copy the program code or program instruction to the main memory, and then initialize the stack, and then initialize the registers, and then jump the and then this then computer processor jumps to the startup routine. So this computer processor calls the instructions included in the this binary code, and then the binary code is started to be executed by processor. So this is the step of loading a program. And then sometimes we use the dynamic linking. So actually in the previous slide, I explained about the static linking. So static linking include all required libraries in the one single binary code. So what is the disadvantage of this static linking? So if we include the very large libraries, the size of the binary code as an execution file it gets larger. But sometimes some libraries, some modules or some functions in the libraries, we do not use some functions or modules included in the library, a certain library. So this is some waste of space in the disk storage devices. So we can use the dynamic linking. So what is the dynamic linking? If the library is requested by the program, then the program dynamically calls this library stored in the disk or some storage devices. So this library is physically stored in the disk drive, so we can save some space for the storage devices. But when loading some code to the main memory will take a long time. So with the dynamic linking, so the execution time of the program maybe gets longer. So this slide shows the effect of compiler optimization. So for example, let me take an example with the GCC. So if we use the GCC compiler for compiling C program, then we can set up some optimization option for GCC. So if we use the -G option, is the unoptimized compilation. So it's actually -G option is used for debugging. This is non-optimization. And then also we set the optimization option with the -O plus some numbers like here. So this number is some optimization level set for GCC compiler. So this graph shows the performance change by this optimization option. So let's see the performance here is a relative performance. So performance. Yeah. So actually for homework number 1, so we have the questions about the performance, and then some students asked so performance difference between performance and the execution time. So actually I explained that. So the performance is the inverse of the execution time. So actually this graph shows the performance. So this is the inverse of the execution time normalized to the baseline. So what is the baseline? It's the non-optimized version. So performance is 1, and then when the optimization 1, so optimization level 1 is applied, the performance is increased by about the 2.4 times. So what does that mean? So this ratio of the execution, the inverse ratio of the execution is increased by 2.4 times. So here, and then O2 and O3 is also similar. So performance is similar with the other optimization level. How about this instruction count? So what are changed by this optimization level? So we know that we learned that we not actually I cannot say we know we learned that what's the execution time? Execution time exit time is the instruction count multiplied by CPI multiplied by clock cycles T. So this is the execution time. So we know that the performance is changed by the optimization level. So what is changed by the compiler? How about the execution time? Instruction count. So we can know that the instruction count is dramatically reduced by optimization level. So it can be many. There may be many reasons. So I cannot explain some compiler techniques here, but when the optimization is applied by the compiler, the number of instruction count, is actually number of instructions is reduced, can be reduced. Yes. Also, as the instruction count is reduced, the clock cycle is also reduced. It's very similar. And how about the CPI? Clock per instruction is increased. So as the CPI is increased, but it is not good for the performance, but why the performance is improved? Because the instruction count is dramatically reduced. So this result show that the compiler applies some complex instructions, but this complex instruction is good for the performance. So we know that the CPI, the clock per instruction is slightly increased, so it's not good for the performance. So here, so if the CPI is increased, the performance may be decreased, but instruction count is dramatically decreased. So overall performance, so is some execution is a proportional. The clock cycle is proportional to the uh, uh, execution time. So as the instruction count is dramatically reduced, the performance is improved by compiler. So this is amazing, right? Also, we can compare the different algorithm or different language and the different compilers. So this is the bubble sort algorithm. So and then this graph shows the relative performance by bubble sort algorithm. So it's a baseline. So compiled by C compiler, and then no optimization is applied. When the optimization level is 1, then so what? The performance is improved by 2.4 times. How about the Java? What is Java? So Java is the virtual Java. For the Java has the virtual machine here, and then so actually when the Java is compiled, the virtual code is generated, and then the virtual machine execute this virtual code like such a similar to the interpreting approach. So let's see the Java. When the same code is compiled by Java compiler, then the performance is also dramatically decreased. So actually, if the Java is applied like with the Java virtual machine, then performance is not good. It's a normal. But when the JIT just in time compiler is applied to the Java application, then we know that the performance is also dramatically improved compared to this normal Java compiler. And how about the quicksort? Quicksort is also different, but we know that we can see that with the bubble sort, the performance is really similar to the different optimization level, but when for the quicksort, the performance actually improved if the optimization level 3 is applied. So here, and then let's see the Java. So what happened to the Java? So even though just in time compiler is applied to the Java code, the performance is less than the performance is lower than the baseline. So code is compiled by the C code. So sometimes the performance of the program is influenced by the program language, and then but we normal we can actually if the program is coded with the assembly code, like assembly code, the performance may be highest, but it's very hard to write very hard to write the code with the assembly code. So normally, if the code is written in C, then performance is very good. But if the code is written in other languages like Python or Java, then performance may be lower than the C program. So it's some difference between the program language and compiler. So let's see the speed up by quicksort. So as the algorithm is changed, so actually the better algorithm is applied to the some same application, then performance can be improved, obviously. So it's obvious actually. So compared to the bubble sort, so this is the baseline with the non-optimized bubble sort. Then when the quick sort is applied, the algorithm is applied, then performance is also dramatically improved. So this result show that the firstly, algorithm is very important for the performance of application. It's very important. So better algorithm will generate better program. That's why we need to learn algorithm course as a computer engineering student. So it's very important actually. So developing a better algorithm is important to increase the performance of computer system as an application. Also, other techniques like compiling optimization can be helpful to improve the performance of application. And then hardware. Hardware is also important to increase the performance. But firstly, the better algorithm is so important. So actually, if you read the textbook, then you can see that some other technique like compiler optimization or better hardware cannot uh, change the DOM algorithm. This some similar contents, you can find the similar contents in the textbook, but it's true. Some very good optimization technique or very good computer hardware cannot change DOM application. So this is what we learned from here. Nothing can fix a DOM algorithm. Nothing can fix a DOM algorithm. So important. So So that's why the programmer's ability is very important to develop the good program, good applications. And then, but also the better better optimization or some better computer hardware is also important to improve the performance of entire uh, computer system. So if the algorithm is the same and some application uh, level is the same, of application algorithm is the same, then only we can apply the compilation optimization, compiler optimization, and then some better hardware or better architecture to improve this system. So this is always normally true. Just-in-time compiler is better than the performance is better than the Java virtual machine. And then compiler optimizations are sensitive to the algorithm. It's a very interesting. Some optimization level is good for some algorithm. Okay, so let's see the array versus compare the array and pointers. If you learn the C programming, then you will be very familiar with the pointer, but pointer is the one of the most difficult part in the C program. So it's very it's not easy to understand the pointer. So pointer is just the address of the variable. So actually the pointer is the address for pointing the main memory. And what is the array? Array is just uh, array is here, and then what is the pointer? Pointer is the int like here. So pointer is the actually this address, and then this array. So actually, when we declare the data type with the array, then array also has the some base address and then indexes. So array is very similar to the pointer, but by the compiler, this array and pointer can be translated into some different, translated differently. So pointer is the directly to the memory address. So when we use the pointers, then we can avoid some indexing complexity. Why? Actually, we use the array, then the array is compiled by the compiler, and the compiler need to calculate some uh, address of each array, like a base address plus I multiplied by element size, like this. But if we use the pointer, then pointer can be directly translated into the memory address. So let's compare these two programs as a so actually the behavior of these two programs is the same. Actually clearing the memory space or clearing or so initializing arrays or clearing some memory spaces. So this function receives the argument with the array and the size of the array. So actually the I is declared, and then by increasing this I, then the element of the array is initialized into the 0. And how about this code? Then this code receives the pointer of the array and the size of the array, and then this function declares the pointer data type, and pointer receives the base address of the array here, and then so it's some upper limit of the some pointer address, and then we increase this pointer, and then this is the pointer, the value stored in the main memory pointed by this pointer address. So we initialize this element of this array with the 0. So the behavior is the same. But let's see the some translated code. So actually you can find there some. So you can see that this auto program is the same because the behavior is the same. So what is different? Actually, this if the array is used, then loop is here. So you know that in this program, this for statement repeatedly execute these instruction. So loop is here, and then this loop repeatedly execute these 5 instructions. But if we see this array, then array inside of the loop, this program include 3 instructions. So why? So if we use the array, then this compiled code need to calculate the address of each array element. But this when the pointer is used, the compiler directly increase the uh, address by the size of the element. So this is somewhat different. So here this code calculate the I multiplied by 8, and then this instruction is included. But in this code, this code directly increase the pointer value, address value by 8. So the behavior is the same, but the execution time, execution performance can be different because actually inside of a loop there are 3 instructions for this code, but for this code inside of the loop there are 5 instructions. So when we compare the number of instructions by these 2 different code, then number of instruction maybe is less for this code when the pointer is used. So can be different. Also the performance can be different. So I already explained about this function, but don't worry about using arrays. Actually, recently the compiler is very advanced. The compiler optimization technique is very advanced. So most of the compiler can apply the optimization techniques. So even though we use this array like this, then compiler can optimize the translated code. So this code just show the unoptimized, so directly translated from the high-level language to the assembly language. So no optimization is applied for this code, but when the optimization technique is applied, then the compiler can reduce the number of instructions inside of the loop, even for this array version of the program. So don't worry about this difference. But I just to show the difference between some directly translated code by array and pointers. Okay. And then now I will briefly introduce the x86 instructions. So actually, we most of us use the x86 based computers because most of us use the the laptop equipping the Intel or AMD CPUs, and then if the Intel and the AMD CPUs is designed based on the x86 architecture. x86 is actually instruction set architecture. So, even though the x86 architecture is widely used, the x86 is CISC, complex instruction set architecture, complex instruction set computer. So it's not easy to learn about the x86 instructions. And then because of the backward compatibility, the number of instructions is also very large with the x86 ISA. So that's why we learned with the uh, RISC type instruction such as MIPS, ARMS, or RISC-V. So actually the RISC type instruction is actually easier to understand compared to the x86 ISA. But I will briefly introduce about the x86 instructions. So this is the history of the x86 instruction set architecture. Actually, this is the first x86 computer is introduced in 1974. It's the 8-bit microprocessor. 8-bit. So, so, so you can expect that this computer is designed in 1974. It's very, very simple computer and very, very low. The performance is very low. So you can see that the clock frequency is about it's one megahertz. Actually it's people, yeah, it's a uh, very wimpy and very simple computer and then 8-bit microprocessor. And then this 8080 used the accumulator and then 3 index register pairs. So they're very simple. And then after 4 years, and then Intel introduced the 16-bit computers called the 8086. So it's in 1978, and then actually this is the first type of the IBM actually the IBM personal computer desktop. And then with this processor this processor is the 16-bit support the 16-bit data type and then 16-bit address type, and then this is the actually the this is the first complex instruction set. Support the first complex instruction set. So actually it's very old. So but it's some first personal computer or first desktop for the some normal users as 8086. And then Intel include the floating point coprocessor. It's not main processor, it's the coprocessor. So it just help to calculate the floating point operations. It's a coprocessor. It's called the 8086 processor. So for this processor, Intel adds the floating point instructions and then register step. So the floating point instruction is just added by 8087 processor. So how the floating point is calculated before 8087 was are the old processors. So using the integer instructions is very so it's hard to imagine, but it's actually it's true. The floating point instructions is calculated based on the integer instructions. And then 8286 is called the AT. It's introduced in 1982, and then it supports the 24-bit addresses. 24-bit memory addresses, and then memory management unit. And then 8386 is a 32-bit extension. So from the 8386 processor, Intel introduced the 32-bit memory address extension. So it's a 32-bit computer, 32-bit processors. So this is called the IA32. So if you are familiar with the Linux, then actually the Linux is still supporting the 32-bit computers, the 32-bit instruction set. Then you can find that the 32-bit libraries or 32-bit binaries has the extensions such as the i386, i386이라고 부르죠. 네. So this is because the first 8386 is designed for the 32-bit instructions, 32-bit memory addresses. So this is the some base instruction set for the 32-bit computers. So this is called the IA32. And then in 486, 사실 그래서 정치인들 386이라고. 486 is introduced in 1989, and then with this processor has the pipeline architecture, and then also this processor supports the on-chip cache. On-chip cache. So actually, the modern processor, the recent processor, include a very large cache memory, but this cache memory is included in the CPU in 1989 by 486 processor. Then so also the floating point execution unit is included in this CPU. Then also Pentium is designed by the Intel processor, and then this Pentium supports the superscalar processing and then 64-bit data path. And then MMX instruction is also included in the Pentium processor. And then this Pentium processor is actually very famous for FDIV bug. So some bug in calculating the divide instruction. So this divide instruction generates some very small, so incorrect, very small errors, incorrect values. So actually, this is the bug by the divider engine, divider execution unit. So actually, Intel tried to hide this bug, and then Intel announced that this bug is ignorable because this bug will not happen frequently. But some economists shows that this bug can happen frequently. So Intel replaced their CPU. So actually fixed this bug and then replaced their CPU with a newer version. But it's a very famous bug. So Intel profit is reduced dramatically. So 손해가 엄청났죠 이때. And then Intel also improved their architecture with the Pentium Pro, and then Pentium 2, and then Pentium 3, and then the Pentium 3, Intel also include some new SSD instructions. So it's a streaming SIMD extensions. So as you can see, as the processor is advanced, Intel, so actually CPU manufacturer, add the more instruction. And then new microprocessor architecture is also designed and improved. So this is some history by the Intel processor, but until the Pentium Pentium processor, so it's a 32-bit computers. And then the first 64-bit computer is introduced by the AMD. So the 64-bit library or 64-bit binary code is called frequently called the AMD 64, because the AMD first introduced some extended architecture for 64-bit computers. So actually, Intel tried to design the actually new 64-bit computer architecture, instruction set architecture called the IA64. But the problem of this IA64 is that it depends on the compiler optimization. Also, the backward compatibility is not guaranteed by the IA64. So actually, I understand the Intel's decision, because the Intel CISC, the x86 architecture is very complex, and then the new instructions are included every year, so it's very hard to uh, design, or it's very hard to improve the microarchitecture of the CPUs. So Intel tried to introduce the new instructions and architecture, and then but for backward compatibility issue, due to the backward compatibility issue, this architecture is not widely used. And then recently, this IA64 Itanium is was retired recently. So AMD introduced the first 64-bit architecture, 64-bit computers, and then Intel also participate in this architecture. Actually, this architecture is called the x86 64. So, so the modern CPUs are like Intel I family and then AMD CPU support the x86 64 instruction set architecture. And after that, Intel and then AMD added the new instructions for multimedia processing, like SSE, SS3, SS4, and SSE5. Also, some better extension. So the problem is that x86 ISA is very complex and complicated, and that because of the backward compatibility. So if you see the some Intel CPU emulator, 굉장히 더러워요. it's very complex. Yeah, so that is true. If Intel didn't extend with compatibility, so backward compatibility, its competitor would. 그러니까 인텔이 하지 않으면 다른 사람이 한다는 거죠. 다른 회사가 한다는 거죠. So technical elegance is not equal to market success. Actually, this is very true in the real world. Technical elegance does not guarantee the market success. 맞죠? 네, 여러분들이 사실은 많은 그 엔지니어들이 좀 생각을 해야 될 그런 문제이긴 합니다. 우리는 엔지니어니까는 그냥 항상 뭐 좋게만 개발을 하려고 하고 있긴 하지만, 사실 마켓에서의 사람들의 선택은 테크니컬리 좋은 거, 테크니컬리 하이한 거를 선택을 하는 것이 아니라, 자기가 뭔가 쓰기 편하고, 그리고 이제 자기가 써왔던 거에 많이 이제 포커스돼 있는 경향이 많이 있습니다. 그래서 사기 쉽지 않아요. 그래서 뭐 테크니컬리 좋다고 하더라도 마켓에서 이제 살아남기 힘들 수가 있고, 이런 건 뭐 역사적으로 많이 있었죠. 뭐 지금은 뭐 애플이 성공한 것도 뭐 애플이 뭐 테크니컬리 뭐 좋은 뛰어나서 뭐 그런 거라기보다는 애플이 시대를 잘 타고나고 이쁘게 만들고 뭐 그런 것도 많이 있죠. 네, 그래서 마켓의 석세스는 뭐 테크니컬리 알레강스랑 똑같지 않다. 예, 참 쉽지 않은 문제입니다. So actually this slide shows some basic x86 registers. So actually the RISC-V has the 32 64-bit register set, but Intel has also very complex register files like this one. So EAX, ECX, EDX, and EBX. So actually this register can be used for some special purpose. Also, the register can be used for the general purpose like this one. Also, Intel was also equipped with some special purpose register like code segment pointer, stack segment pointer like this one, and then PC and then condition code like this one. So Intel register is actually the not as easy as understand. It's not easy to understand the Intel register file structure, and this is just the revealed for the programmers. And then it's some revealed architecture for assembler programs and the compiler designers. And then the physical address can be different inside of the Intel CPU. And then let's see the E flags. This is the condition code, and this condition similar condition registers can be found in the ARM processor. 그래서 뭐 같은 ARM 아키텍처가 이제 리스크긴 하지만은 ARM 아키텍처는 지금 뭐 우리가 배웠는 리스크 5나 아니면 밉스 아키텍처랑도 또 다릅니다. 그런 차이가 있어요. So I said that the x86 is the CISC architecture. So actually this x86 support the some various some memory instructions. So for example, the memory can be directly accessed by the arithmetic operations. Also, memory addressing mode is the complex. And then it's a CISC. It's the some feature of the CISC. CISC, the instruction length can be different. So variable length encoding. So postfix byte specify the addressing mode, and prefix byte modify the operation. It's very complex. So 다행이죠. 여러분들이 지금 리스크로 배운다는 것이 다행입니다. So yeah, so instructions can have a variable length. So the decoder implementation is very hard for the x86 architecture. So what is the advantage of this variable length? So we can increase the code density. So that means that within the some same memory space, we can include more instructions because the instruction length is variable. It's a various. But actually, the Intel also inside of the Intel CPU, the Intel also applied some risk-like microarchitecture. The problem of the x86 is that complex instruction set is a complex instruction set, so makes implementation difficult, very difficult. So as I said, so Intel make the microcode translator, and then this microcode translate the complex instruction into simple many instructions. So translate this is the some operation of the microcode. So actually, even though this Intel CPU support the very complex instructions, this microcode translate this complex instruction into many simple instructions. And then, so inside of the Intel CPU, the architecture of the Intel CPU is also similar to the architecture of the RISC type CPU. So micro engine is similar to RISC. So simple instruction. So Intel is a one-to-one and one-to-many instructions here. So actually 그래서 인텔은 CISC 인스트럭션을 받지만은 그 내부는 리스크처럼 돌아간다라고 보시면 됩니다. 여기에 트랜슬레이터가 있고 CISC를 심플한 인스트럭션으로 이제 바꾸게 되는 거죠. So the performance is improved, and then recently the performance of the Intel CPU is higher than the other RISC process actually. So it's because the Intel microarchitecture has some advanced has the advanced architecture, and also Intel CPU apply the RISC-like architecture. So I will conclude this chapter, the design principle of the instruction set architecture. Simplicity favors regularity, and the smaller is faster. A good design demands good compromise. So this is the good design principles for the instruction set architecture. Actually, as I believe that these design principles can reflect some RISC design principles, but we know that CISC is very complex. So, and then modern CPUs, even though x86 CPUs has the RISC-like architecture. So actually, this is true for the old instruction set architecture. Okay, and then also it's important to make the common case fast. It's very important in the computer system or applications. And then also we learned about how the high-level language program is translated and then started on the executed in the computer system. Okay, I will stop here, and then I will try to post the homework today, but due to some special issue or some close of my office, then the homework may be posted later. But please monitor the Blackboard or Piazza, and then if the homework is posted, then try to try to do homework early. 네, 수고 많았습니다. 그 호목을 오늘 올릴 예정인데 뭐 올릴 수 있을지 잘 모르겠습니다. 그렇지만 어쨌든 호목이 올라오면은 뭐 저번과 같이 그 호목 그렇게 이제 잘 해주시고 그리고 이제 여러분들이 네, 여러분들이 그 호목을 카피를 그러니까 카피란 게 제가 이제 PDF를 올리면은 그거를 그냥 카피 앤 페이스트 해가지고 워드로 옮겨서 하다 보니까는 뭐 이렇게 10의 6승, 10 to 6 같은 10의 6승이 106으로 이제 카피가 돼가지고 좀 잘못 푸는 경우가 많이 있는 것 같은데요. 네, 어쨌든 그런 그 실수, 미스테이크들을 뭐 줄일 수 있도록 좀 체크를 하면 좋을 것 같습니다. 채점할 때는 조교가 이제 채점할 때는 뭐 그렇게 잘못 카피 앤 페이스트 해서 뭐 10의 6성을 106으로 계산한 것도 다 맞긴 해줬지만 제가 좀 굳이 뭐 문제를 카피를 해서 그렇게 할 필요는 할 거 없고 그냥 답만 써서 제출을 해도 뭐 됩니다. 그러니까는 이런 실수를 잘 하지 않도록 체크를 하시기 바랍니다. 예, 수고 많았습니다. 다음에는 얼굴도 인클루드 하도록 하겠습니다. 뭐 보는 걸 좋아할지 모르겠지만, 예, 다음에